The universe is 13.8 billion years old. That's a fact. And in those 13.8 billion years, there are rules about how big things can get and how fast they can grow. Black holes follow these rules like everything else. They start small and they grow by consuming matter, and there's a maximum speed limit for how fast they can eat and how massive they can become. Scientists call this limit the Eddington limit, and it's based on simple physics. Even if a black hole started eating the moment the universe was born and never stopped feeding for 13.8 billion years, it could only grow to about 10 billion times the mass of our Sun. That's the absolute maximum, the biggest a black hole can possibly be. But astronomers have found something that breaks this rule. In 2010, scientists at the South Pole Telescope in Antarctica detected something impossible: a black hole 5.8 billion light-years away that weighs 100 billion times the mass of the Sun, 10 times heavier than the maximum possible limit. And when they measured how fast it was growing, they found something even stranger. This black hole is still feeding right now, the monster that breaks physics. The black hole is called Phoenix A, and it sits at the center of a massive galaxy cluster, and it's so large that trying to comprehend its size breaks your brain. To understand just how massive this thing is, you need to start with something familiar and work your way up. Our Sun weighs about 2 trillion kilograms. That's a 2 with 30 zeros after it. The Sun is so massive that it contains 99.8% of all the matter in our entire solar system. Every planet and moon and asteroid and comet combined only makes up the remaining 0.2%. The Sun is basically everything. Now imagine taking 100 billion of those suns and crushing them all down into a single point in space. That's Phoenix A. The black hole at the center of our own Milky Way galaxy is called Sagittarius A star, and it weighs about 4 million times the mass of the Sun, and scientists thought that was big. But Phoenix A is 25,100 times more massive than our galaxy's black hole. If you replaced Sagittarius A star with Phoenix A, the event horizon would extend past the orbit of Pluto, and it would swallow our entire solar system, and we wouldn't even notice it happening because we'd be dead long before we got close enough to see it. The event horizon is the point of no return, and once you cross it, not even light can escape. For Phoenix A, that boundary sits 366 billion miles away from the center. To put that in perspective, if you were traveling at the speed of light, which is 186,000 miles per second, it would take you 71 days to cross from one side of the event horizon to the other. Just the edge of this black hole is bigger than most solar systems, and it's not just sitting there, it's growing. Right now, at this very moment, Phoenix A is consuming matter at a rate of about 60 solar masses per year. That means every single year, this black hole eats the equivalent of 60 suns and adds that mass to itself, and the process never stops. By the time you finish watching this video, Phoenix A will have consumed thousands of tons of matter and converted it into pure gravitational energy. But here's the problem. The black hole shouldn't exist in the first place. The Eddington limit exists because of radiation pressure. When a black hole feeds, it doesn't just suck in matter like a vacuum cleaner. The matter gets superheated as it falls toward the event horizon, and it releases massive amounts of energy in the form of radiation, and that radiation pushes back against anything trying to fall in. It's like trying to walk into a hurricane. The closer you get, the harder the wind pushes you away. This creates a natural speed limit for how fast a black hole can grow. If it tries to eat too much too fast, the radiation pressure becomes so strong that it blows away the surrounding matter, and the black hole can't feed anymore. Scientists have calculated this limit very precisely, and it means that even under perfect conditions where a black hole has unlimited food and nothing gets in its way, it can only grow at a certain rate. And that rate maxes out at about 10 billion solar masses over the entire lifetime of the universe. Phoenix A weighs 100 billion solar masses, 10 times more than the absolute theoretical maximum. The math doesn't work, and there's no natural explanation for how this thing got so big. Either the laws of physics are wrong, or something very strange happened in the early universe that we don't understand yet, or both. But the impossible size isn't even the strangest part. The star factory, Phoenix A, sits at the center of a galaxy cluster called the Phoenix Cluster, and this cluster is doing something that black holes are absolutely not supposed to allow. It's creating stars at an incredible rate, and this shouldn't be possible because black holes are supposed to be star killers. Here's how it normally works. When a supermassive black hole sits at the center of a galaxy, it heats up all the gas around it to temperatures of millions of degrees. That heat prevents the gas from cooling down and collapsing into dense clouds, and without dense clouds, you can't form stars. The black hole essentially sterilizes the entire region around it and shuts down star formation completely. This is what we see everywhere else in the universe. Galaxies with active supermassive black holes at their centers have almost no star formation happening. The black hole acts like a thermostat that keeps everything too hot to make stars. Scientists call this black hole feedback, and it's one of the main ways that galaxies regulate their own growth. But the Phoenix cluster is doing the opposite. The cluster is forming about 740 stars per year. To put that in perspective, our entire Milky Way galaxy forms about 1 or 2 new stars per year. The Phoenix cluster is creating stars at a rate 740 times faster than our galaxy, and it's doing this despite having one of the most massive black holes ever discovered, sitting right in the middle of it. It's like finding a wildfire that stopped burning and started growing a forest instead. Scientists were baffled when they first discovered this, and they spent years trying to figure out what was going on. How could a black hole this massive allow so much star formation to happen? Every model they ran said it should be impossible, and every observation they made confirmed that it was happening anyway. And then in 2025, they found the answer, or at least part of it. The black hole is weakened. Somehow, Phoenix A has lost control of its surroundings, and the galaxy is taking advantage of that weakness to create stars at a massive rate. But scientists didn't know how this happened, or why the black hole was weak, until the James Webb Space Telescope took a closer look. The missing link. For years, scientists had a major problem when studying the Phoenix cluster. They could see extremely hot gas near the black hole with temperatures over 1 million degrees Kelvin, and they could see extremely cold gas farther out with temperatures around 10 Kelvin, which is just barely above absolute zero. And that cold gas is what was forming into stars. But there was nothing in between. No warm gas, no medium temperature clouds, just a massive gap between the million-degree plasma near the black hole and the near-frozen gas forming stars. It was like finding boiling water sitting right next to ice with no lukewarm water anywhere in the middle. That shouldn't be possible because heat doesn't work that way. Energy should flow from hot to cold and create a gradient of temperatures. Scientists called this the missing link, and it was one of the biggest mysteries about the Phoenix cluster. Where did all the medium temperature gas go? And how was the cold gas staying cold when it was sitting so close to a black hole pumping out massive amounts of heat? In 2025, the James Webb Space Telescope found the answer. Webb detected something that previous telescopes had missed, a massive flow of warm gas sitting right between the hot and cold zones, and this gas wasn't just sitting there, it was moving, flowing. About 10 billion solar masses worth of gas was streaming away from the black hole and cooling down as it moved and forming into long filaments that stretched across the cluster. These filaments are where the stars are forming. The gas cools from 1 million degrees down to about 10,000 degrees as it flows through the filaments, and then it cools even further down to 10 Kelvin and collapses into dense clouds, and those clouds ignite into new stars. The entire process happens in a continuous stream, and that's why the cluster can form so many stars so quickly. But this creates another question. Why is the gas able to escape from the black hole in the first place? Normally, a supermassive black hole keeps all the surrounding gas trapped in a cycle where it heats up and then cools down and then heats up again and never escapes. The black hole maintains control and prevents star formation. Phoenix A has lost that control. The black hole is pumping out energy, but not enough energy to keep the gas trapped, and scientists don't know why. The leading theory is that we're witnessing a very brief window in the black hole's lifetime where something went wrong and it weakened temporarily. And that window won't stay open forever. When the monster wakes up, right now, Phoenix A is in a weakened state, and that weakness is allowing the Phoenix cluster to create 740 stars per year, and it's allowing scientists to study a process that normally doesn't happen around supermassive black holes. But this state is temporary, and eventually the black hole will regain control. When that happens, the star formation will stop. The black hole will heat the surrounding gas back up to millions of degrees, and the gas won't be able to cool down anymore, and the filaments will evaporate, and the stars will stop forming. The Phoenix cluster will go quiet, and it'll look like every other galaxy cluster with an active supermassive black hole at its center. Scientists don't know when this will happen. It could be in 1,000,000 years, or it could be in 1 billion years, or it could have already happened and we just haven't seen it yet, because the light takes 5.8 billion years to reach us. We're seeing Phoenix A as it was 5.8 billion years ago, and not as it is today. And by the time we see what happens next, another 5.8 billion years will have passed. But what we do know is that we're witnessing something incredibly rare, a supermassive black hole that somehow got 10 times bigger than physics says it should be, and somehow lost control of its surroundings and allowed a massive burst of star formation to happen. This combination of events might only happen once in the entire history of the universe, and the fact that Phoenix A exists at all forces scientists to rethink everything they thought they knew about how black holes grow. None of the existing theories can fully explain it, and every new theory creates more questions than it answers. Some scientists think Phoenix A might have formed from a direct collapse event where a massive cloud of gas in the early universe collapsed straight into a black hole without forming a star first. That would give it a head start on growth and allow it to become much larger than normal black holes. But even with a head start, the numbers still don't add up to 100 billion solar masses. Others think it might have formed from a merger of smaller black holes in the very early universe, and those black holes combined into one supermassive object. But we've never observed anything like this happening, and the models don't predict it should create something this large. And some think Phoenix A might have broken the Eddington limit and fed faster than physics says it should be able to. But we don't know of any mechanism that would allow this to happen, and every observation we've made of other black holes shows they all follow the Eddington limit pretty strictly. The truth is probably some combination of all three theories, or it's something completely different that we haven't thought of yet. What we do know is that Phoenix A exists, and it's real, and it's forcing us to admit that the early universe was more violent and more extreme than we thought, and that black holes can grow in ways we don't fully understand. Phoenix A even created a new category of objects that scientists call stupendously large black holes, or slabs. And if one of these exists, then there might be more of them out there that we haven't found yet. And every single one of them is a mystery waiting to be solved. Right now, 5.8 billion light-years away, Phoenix A is still there, still feeding, still growing, still creating stars at a rate that shouldn't be possible. And in a few 100 million or billion years, it'll wake up and shut down the star factory and reclaim control of its galaxy cluster. But for now, for this brief moment in cosmic history, we get to watch the largest black hole ever discovered doing something it's not supposed to do. And maybe that's the real lesson here, that the universe is bigger and stranger and more extreme than we ever imagined, and sometimes the rules we think are ironclad turn out to be more like suggestions. Phoenix proves that even our best theories about how the universe works can be wrong, and there are still mysteries out there that we can't explain. So what do you think happens when Phoenix A regains control and shuts down the star formation? Do those 740 stars per year just stop forming, or does something more dramatic happen? Let me know in the comments. And if this changed how you think about black holes, hit that like button and share this with someone who still thinks black holes just suck everything in. Thanks for watching.